Okay, we'll get started and welcome. Happy Monday, everybody. I hope your weekend was good. And I've posted our first homework assignment, and that's available under a week 2. And you know, it's as per tradition, it's fairly lengthy, so I recommend getting started on it as soon as possible. And yeah, you know, as you come across questions, post them on Campus Wire, and we'll try to help each other out. All right, so today I am going to talk about cross-validation. Okay, cross-validation is a strategy that we can use to compare models as a way for model selection. Okay. So we're going to take a look, continue looking at this Olympics data set, right? So again, we're looking at the 100 meters race time, and what we've noticed is that as time has gone on, the people have run the race faster. The gold medal time has gotten faster and faster. Okay, and so we did this last week on Friday. We tried fitting a whole bunch of different models. These are just polynomial models. So we have a linear model, a polynomial, you know, quadratic, cubic, 4th order, 5th order, and 6th order polynomials. And I've just called all of these poly 2, poly 3, poly 4, poly 5, okay? And all of these just have LM, and we're just trying to predict the time based on X being Olympic $year, okay? So X being the kind of the year column in the Olympics data set, okay? And then for each of these, we are going to plot the fitted values, okay? And we're going to get different lines, okay? So so the dots represent the original data, and then and we've plot all of these different things, okay? And so we left off on Friday just talking about, you know, looking at the summary tables and looking at the AIC and BIC values. And some students asked if, you know, they said, you know, I never actually took 101A, and so I'm not too familiar with AIC and BIC. And my answer to that is don't stress about it, okay? I only presented AIC and BIC as a contrast to cross-validation, okay? So those are some of the tools that were covered in kind of your classical 101A course, and those, you know, there's different ways to calculate them that kind of take into account model complexity. All right, so as we increase the you know, the degree of our polynomial, we're going to have more coefficients to estimate, and every time you estimate another coefficient, you use an additional degree of freedom, right? And in general, we kind of want the best bang for our buck. If we think of degrees of freedom as kind of a budget, you know, you don't want to have a model that with too many of these things, okay? The classical approach often requires thinking, okay? And so, so I wrote, does it make sense for race times to have a quadratic or cubic relationship to time? Does it make sense for there to be a 6th order polynomial relationship to time? Okay, and these are really hard to answer. It's hard to even reason or think about, okay? And again, you know, we have tools like AIC or BIC to aid in this model selection procedure. And today we're going to look at cross-validation, okay? Cross-validation avoids a lot of this thinking that we have to do, okay? And that could either be a good thing or a bad thing, okay? You know, it's always good to be thinking, but sometimes when it comes down to thinking and you don't know a whole lot, then the thinking just becomes arbitrary. So so if you are skilled and knowledgeable, then yes, you should rely on your thinking and instincts, okay? But if you're not, then sometimes it's good to avoid arbitrary decision making, okay? And so we're going to use this validation set strategy. And so what cross-validation does is it splits the observed data into two parts. Okay, you've got a training set and a validation set. And what we do is we use the training set to fit the model. Fitting the model means finding your coefficients, whether that be the slope and intercept, or if you've got a more complex, model, estimating the, all of the other coefficients as well. Okay, and then so you figure out what the slope and intercept and other values should be on the training set, and then once you have those, okay, after fitting the model by using the training set, you use those estimated parameters to make predictions on the validation set. Okay, so and then we've got some kind of metric. Mean squared error is often a common choice. You got some kind of metric that measures how well did your estimated model make predictions on the validation set. Okay, how well did it work? Okay, and then and you do this for each different kind of model, and you can kind of choose the best performing one. Okay, so so we're going to just start off with leave one out. Okay, leave one out cross validation, and in this set or in this strategy, basically your training set's going to be all of the data points with the exception of one. You leave one of them out. Okay, that one that you left out is going to be your validation set, right? And you do this for every single data point in your in your data. Okay, so if you have 70 observations, you're going to have 70 different training and validation splits. Okay, it's going to be observations 1 through 69 is the training, observation 70 is the validation. Then it'll be observations 1 through 68 and 70 is your training, and then observation 69 is the validation set. And then so on and so forth. Observation 68 will be the validation set, and whatnot. Okay, so here I've got just this very toy data set. Okay, 4 data points, 1, 2, 3, 4, compared to 1, 3, 2, 4. All right, and what we're going to do is we're going to do leave one out cross validation. Okay, so the training set is going to be observations 1, 2, 3. X will be 1, 2, and 3, and then we're going to leave observation number 4 as the validation set. Okay, so I'm going to specify indexes 1, 2, 3 as the set that I'm going to use for my training. Okay, so I'm going to subset X using indexes 1, 2, 3, and then I subset T using indexes 1, 2, 3. And then the validation will be everything except the the indices that I've chosen. Okay, so the validations I'm going to subtract off, exclude observations 1, 2, 3. So that will leave observation 4 as my validation X and my validation T. Okay, and what I do is I'm going to create my training data by taking the training X and the training T, and I'm going to fit my data. Okay, where I'm predicting, where I'm going to predict T based on X using the training data. Okay, and so here is, this is what the original data set looks like. Observations, 1, 2, 3, 4, and the T is 1, 3, 2, 4. So this is what the full observation, full set of data look like. Okay, and what happens is in our first run, observation 4 is our validation set. So I really only have these 3 observations. Okay, so I'm fitting a model onto these 3 observations. Okay, so this is the slope and intercept. This line, this is the prediction line if these are the only data points that I have in my data. Okay, if I only had observations 1, 2, and 3, this is the line that I would fit. Okay, and so how cross-validation works is we fit it on these 3 points, and then the one that I left out, this is my validation point, I'm going to measure how much error did I make. Okay, how much error did I make? And so according to this model, I would have predicted 3. The actual value is 4. And so my squared error is equal to 1. Okay, so the error that I've made here is 1. And so for each train validation split, we're going to figure out your predicted value, and you're going to calculate the squared deviation. Okay, so earlier I said the model, the leave one out model, is we predict t based on x using the training data, and then using this model, I'm going to use R's predict command. Okay, and the new data that I'm going to predict for is my validation point. Okay, and so this is going to be my t hat, or my predicted value, the fitted value, and the squared error is going to be the difference between the actual value of t versus my predicted value of t. Okay, and so I take the difference there and I square it, and that's going to be my squared error. And the total squared error, it starts off at 0, but I'm going to do this. So total squared error starts off at 0, but inside I'm going to do this basically as a loop, and I'm going to add this, my squared error, to the total squared error and update my total squared error in this way. So again, here it is. This is all 4 data points. This is what the model would predict if I use training points 1, 2, and 4. So I've left out data point number 3. Okay, so this, if I remove this data point, okay, this is how the line would fit. And I can throw this data point back in, and I can measure how far off is the prediction. Okay, and so here's my my residual, and when I square that, my squared error is 1.6531. Okay, and I'm going to do this for all. Each data point gets a turn being the validation set. Okay, so if I remove this data point, okay, if I remove this data point, then this is how the line would fit. Okay, the least squares line would fit onto these 3 data points. Looks like this. Okay, we look at the data point that we left out, the validation set, and we'll measure the squared error. Okay, whoops. Okay, oh, I'm sorry, I missed a question here. Okay, May asked, can you explain the validation training set for 70 observations once again? Yeah, so each turn will get, each observation will get a turn at being the validation set. So I'm kind of doing it for these 4, okay? So this is the 4 data points, and we started off, I'm just rewinding here, okay? First, it's going to be this observation is the validation set. So we train on the remaining 3, or if it's 70 observations, you train on the remaining 69, and then you throw that one data point back in and you measure the squared error. Okay, here's all 4 data points. You remove the next one, okay, this one. You train on the remaining 3, you throw it back in, and as a, how well did you predict this, and you measure the squared error. Here's all 4 again. This time we're going to go down to the next point. We're going to remove that one. This is the fitted line for these 3, and we see how much error did we make here. Okay, and then lastly, again, here it is on all data points. We're going to remove this 4th data point right here. Okay, this one will go away, and when you fit a straight line on the remaining 3, this is the line you get. And you say, okay, well, how much error did you make? And we get this. All right. Okay. So if everyone's following me, or if you're following me, give me a green check to if you understand this concept of leave one out cross-validation. The idea of removing one data point, fitting the line on the remaining 3, okay, or figuring out how to predict, fitting your model on the remaining ones, and then throwing it back in to get how much error there is. Okay, 45 of you have said yes. 45 out of 60, I guess. Yes, that's okay. Oh, let me give you the first quiz question. Okay, the first quiz question Let me see. On second week Monday, the first quiz question is E as in elephant. Question 1, E as in elephant. Okay, so if you've been keeping track, we had a squared error of 1 on this one, squared error of 1.6531, 1.6531, and then back here we had a squared error of 1. So if you add all of those together, the total squared error is going to be 5.306. Okay, 5.306. That's for the validation, leave one out cross-validation error. And then we're going to divide that by 4, and we get this number, 1.3265. Okay, so this is kind of the average squared error for each data point when we did leave one out cross-validation. Okay, now this all by itself, this number all by itself is not useful, okay, or is not very useful. I mean, it's useful, but it's not, the ultimate purpose of this is that we would do this kind of strategy again, but not with a linear model, but with a different kind of model, okay? And you would go through the process and you would get another mean squared error or some kind of value there, okay? There is a function in R inside library boot called cv.glm, okay? And basically, you fit a linear model or whatever kind of model you want, all right, using the GLM function. And then you run leave one out cross-validation here, okay? You go, you do cv.glm, and this will do leave one out cross-validation by default. You can specify a k for k-fold cross-validation, which we'll cover later. And when you do the calculations, it gives us 1.326531, okay? Which is the same value that we got when we calculated it manually, okay? So, so if you followed my earlier slides, you can see how we arrived at this number, 1.326531, and when we use R's cv.glm function, it also provides us the same number, okay? So in normal cases, you would just use this. You wouldn't use, you wouldn't conduct leave one out cross-validation by hand or, you know, code it up from scratch, okay? All right, how does GLM differ from LM, Tanmay asks. So GLM and LM are very similar if you do not specify family, okay? So family allows you to specify things like the errors are from the Gaussian family, which is kind of your normal least squares errors, but you can also specify that it comes from the binomial family or some other kind of thing. And basically, GLM is for generalized linear models, which allows you to, you know, do logistic regression and other things like that. If you are enrolled in 100C, you will cover the different GLM kind of families there. And basically, there's a linear part where each. Okay, I don't need to get into it. Okay, but pretty much. If you do GLM and you don't specify family, it behaves almost the same as LM, except there's a few other features that allows these packages like boot to give us something cv.glm to do cross-validation for us, okay? All right, so I hope we're okay regarding how we arrived at this number, 1.3265, and so that when you run in production, okay, so part of your homework is you're going to calculate the leave one out cross-validation manually, okay? That's part of your homework. But the idea is that, you know, when you start working or whatever and you have to do cross-validation, you're going to use this code, but at least you'll have an understanding of where this number comes from. It's not some mystery. If someone says, how did this come up with this number, you can explain where this number comes from, okay? And sometimes students get confused, and so I just want to provide some clarification here, is that when you do cross-validation to evaluate a model, you're going to get that single cross-validation score like this, 1.3265, okay? And in our data set where we had 4 data points, we performed leave one out cross-validation, and that requires us to fit the model n different times. In our case, we fit the model 4 different times, each time leaving out a different data point, okay? And then we took those values, added them up, and divided by 4, okay? And so the total cross-validation score, this number 1.3265, is this total divided by 4, okay? And it's the mean of those 4 values, right? So here, again, here's kind of a picture of all 4 of those things. We drew the line based on these 3 points, and this was our squared error. We drew the line on these 3 points, this was our squared error. We drew the line on these 3 points, and this is our squared error. We drew the line. And so when you add all of these up, you get 5.306. When you take the average of these things, you get 1.326. Okay, so after fitting the model n times, you take the mean squared error and you get 1.326. You could try a different model and you would fit that different kind of model n times, and you would get another cross-validation score. And so you're comparing this mean squared error for the linear model to a different kind of model to get a mean squared error there. Okay, and so I'm going to illustrate that for kind of the Olympics data set, I believe, okay? And so I guess before I get into that, I'm gonna just kind of extend this into k-fold cross-validation, okay? And so k-fold cross-validation is similar, except you don't leave one data point out at a time, okay? So if you have a big data set with n data points, you're gonna have to do this process, right? Leaving a data point out, okay, and making a prediction. You're gonna have to do that n different times, right? And so if you've got, you know, 1,000,000 data points, having to fit the model 1,000,000 times is gonna be computationally expensive. So, so you don't really wanna do that, okay? And then the other problem is that because every single model that you fit is fit on everything but one data point, the resulting models often end up looking very, very similar to each other, okay? So the coefficients end up very highly correlated and are also likely to kind of overfit the training data, just because you've got pretty much the data that you're using on the training set is almost identical to the full training data, right? So, so an alternative is to use k-fold cross-validation. Okay? And what this is going to do is it's going to take the data and it partitions the data into, you know, about k equally sized blocks. Okay, and obviously if it doesn't divide into k equally, then it's going to be approximately equal. All right, and one block is going to serve as the validation set, and then the remaining blocks combined to be the training data. All right, so here's kind of an illustration, is that if you do 4-fold cross-validation, all right, you take the entire training set and you divide it into 4 chunks, okay? And during the first iteration, these 3 chunks are going to be the training data, and then this will serve as the validation data, right? So you're going to use these observations to form your coefficient predictions, or coefficient estimates, and use those to make predictions. You're going to predict the validation set and calculate error. Iteration 2, then the second chunk, or the second fold, serves as the validation set, and the remaining 3 serves as the training sets. In iteration 3, you know, this one's going to be the validation, the remaining ones are the training, and in the last iteration, this last set is going to be the validation data, and the remaining 3 will be your training data sets. Okay, and again, training is used to estimate the coefficients, and we use those estimated coefficients to make predictions on the validation set. All right, so let's take a look at the Olympic data once again. Okay, so in our Olympic data, we have a total of 28 observations. 28 observations going from 1896 to like 2012 for the different Olympic Games. Okay, and so this is what it looks like. all right? And this is how we're going to use k-fold cross-validation, okay? So k-fold cross-validation is very similar to leave one out, except you are leaving out several data points rather than just one, okay? All right, and so what we're gonna do is we're going to divide the data into 4 random blocks, okay? So I've got 28 observations total, so I'm going to do 4-fold cross-validation, which means we're going to create 4 random sets of points, okay? And so just in any one validation set, 7 observations will be left out, okay? And then for each of these, okay, so for each training and validation split, okay, and we have 4 of them, we're gonna fit several possible models, okay? And so just to keep everything simple, I'm gonna do just different polynomial models. Again, probably in some other situation, you might try to fit, you know, models where you've transformed the variables. You might transform the x into a log or the y into a log or something like that. And you'll encounter that in the homework, okay? And so this is what we're gonna do. We're gonna fit a linear model, we're gonna fit a quadratic, a cubic, a 4th order polynomial, 5th order, an 8th order polynomial, and just for fun, we're gonna try out a 17th order polynomial, just so you can see kind of how ridiculous having such a super high order polynomial is, right? And for each of these things, what we're gonna do is we're gonna calculate the total squared error for each validation set, okay? And we're gonna do it for each of these models. We're gonna run the same validation set through each of these models. And then after you do that, you're gonna calculate the cross-validation score by averaging the squared error for each model, okay? And at the very end, we're gonna compare the cross-validation scores to kind of help us select which model is the best. Okay, so this is just kind of how I'm going to do this, all right? Now, this is me doing cross-validation manually, okay? And again, in a real-life work setting, you would use the packaged function, cv.glm, to do your cross-validation. But I'm doing it manually, and you're gonna do it manually in your homework, kind of as a learning experience, so you can understand how it works and explain it to other people as well. So here I'm gonna, we had a total of 28 observations, so I'm gonna just take the values 1 through 28, and I'm gonna shuffle them, right? Sample 1:28 is gonna just shuffle these things, okay? And after I shuffle them, I'm gonna take the first 7 and throw them to set A, the next 7 to set B, the next 7 to set C, and the last 7 into set D, okay? So I've shuffled them, and I'm taking, just kind of dealing out 4 piles of 7, okay? And so I've got kind of 4 random sets of 7, and we're gonna call these set A, set B, set C, set D, into a list called sets. Is that all right? And then in order for us to keep track of the cross-validation errors, I'm gonna create kind of empty vectors where I'm going to store this, okay? And each of them have a length of 4 because I'm doing 4-fold cross-validation, which means I'm gonna fit the model 4 times. All right, and so this is what a loop might look like, okay? And so I have this kind of in larger text, and then on the next slide, I kind of write a little bit more, okay? And so here, I call this my validation index, all right? And what I'm gonna do is I'm gonna take kind of the first set, okay? So when I do for I in 1 through 4, we're gonna start off with I equals 1. I'm gonna take the first set, which back here is set A. These are just kind of my first random pile of 7 values. And those I'm gonna say, these are my validation observations, okay? And again, if any of these steps in my code don't make sense to you, just give me a red X and I can happily explain or something, okay? So I'm gonna take that pile of 7 and say, these are gonna be my validation index, all right? And I'm gonna create my training data, okay? My training X and my training T by taking all of, in this case, all 28 years and then removing the data in the validation set, okay? Why did I use double square brackets? Because sets is a list and I want the contents of the list, right? So if I used single square brackets, then it would return back a list with a vector inside. By doing double square brackets, I'm gonna get the actual vector that's inside and not just a list that contains a vector. Okay. Okay, so I take the validation index, I remove the validation indices from the year, I remove the validation indices from time to create my training X and training T. Okay, and then as far as the validation set, I'm gonna take, just take only the validation index for year and only the validation index for time, okay? And then I'm going to put those together into a data frame to create my training data. I'm going to put the validation X and validation T together in a data frame to create my validation data. Okay. And then the number of observations is the length of my validation index, which in our case is going to be 7 for each of these things. Okay. All right. And so how do I do this? Well, first I'm going to fit my first linear model, which is going to be predict. We're going to just do simple linear regression, which is predict T based on X. Okay. And I use the training data. I'm not using all the data. I'm just using only the training data, right? And then I make predictions. I make predictions using this model that I just estimated, right? So I create a linear model to create model 1. And using model 1, I'm going to make predictions for the validation data. Okay, using my new data is validation. Okay. What's the difference between using a semicolon and a new line in this case? No difference, okay? It's generally considered not good style to use semicolons, but I wanted to get enough lines to fit on the page, so I used a semicolon, okay? But a lot of times, you know, the general recommendation, don't use semicolons. It makes your code a little bit harder to read, but I made a stylistic choice in order to get more lines to fit on the page. Okay, so so here I'm using predict. Okay, I guess there is an assumption, a slight assumption, that you are familiar enough with the LM function to create models, and you're familiar enough with predict to kind of make predictions based on a model that you've created earlier. Okay, so we are making predictions for the validation data. Okay, and then to calculate my squared error, I'm going to take the difference between the actual T values, okay, the actual values in the validation data, and the predictions that we are making. Okay, so this is the actual values in the validation set. And these are the predictions that we just made here, right? So I made these predictions T hat for model 1, and I'm taking those differences. I take that and I square it, I sum them up, and I divide by n, in this case 7, okay? And then I'm going to do that for the second order polynomial. And so again, we're still in the same iteration of the loop, okay, where I have the same 7 observations, okay, in my validation set, and then the remaining 21 are in my training set. So I create a model, a second order polynomial model using polyx2, right here using the training data. Using this model 2, which we just fit, I'm going to make predictions using the validation data to get T hat 2. And then I'm going to take those differences, take the differences between the actual, and then square them, sum them up, and divide by n. And I'm storing these into kind of into their locations. All right, and then the next slide, basically I do the same thing. Okay, so this is just kind of like a zoomed in version of this, and this is zoomed out. And I do this for polynomial order 3, 4, 5, 8, and polynomial order 17, okay? So I just do the same thing, but for all the different things. Okay, does this code make sense to you guys, what I'm doing? All right, give me a green check if you're good, and a red X if you are not good. All right, what exactly does T mean in the data frame? Okay, yeah, I'm just following the notation in the textbook. in the textbook, instead of using X and Y, for whatever reason, they've chosen T, okay? So the actual values are T, and the predicted values would be T hat. I know traditionally you're accustomed to using X and Y, but the textbook uses X and T for whatever reason. Okay, why do train and valid have to be data frames? Okay, well, the way the LM and the predict functions in R work is that they are designed to work with data frames. So when you ask predict to make predictions on new data, okay, because if you just do predict on model 1, it'll show you the predictions for all of the observed data points in your data. But here you can do predict on the validation set, and the way R anticipates is that the validation set, this new data is in a data frame in general. I mean, technically, you could provide it different kinds of things, but often it expects a list or a data frame. So that's why they're data frames. Okay, so I do this, and okay, so I just want to show you a bunch of graphs to kind of illustrate what's happening. Okay, so here is, so remember we did k-fold cross-validation. So I've just, I chose set C because I thought this was kind of visually one of the most interesting validation sets. Okay, and so in our training, in our data, okay, I did k-fold cross-validation just in this run. Okay. For set C, these are the 7 points, 1, 2, 3, 4, 5, 6, 7. These 7 red points happen to be in the validation set, okay? Again, all we did was we shuffled these observations up and we dealt them out into 4 piles. Each pile is gonna have 7 observations in them. And in this case, these 7 observations happen to be the observations in set C. Okay, and so again, the strategy is we are going to remove these 7 dots in the validation set, and the remaining 21 points will serve as our training data. Okay, and I'm going to fit a linear model. So I've removed those 7 observations, and these are my training data. Okay, and now what I'm going to do is I'm going to look at those 7 red dots and calculate how much error is there between this line. This is the line that we've created to predict these 21 training data points, okay? And if this is the fitted value, and now I'm going to use them to make predictions on those 7 red points that I've left out, okay? So here's our full set. I remove the 7 and I fit a straight line. And then I go back to those 7 red points that I left off and I say, well, how well did it predict, okay? And it actually did quite good. It did quite well for these, okay? So maybe by coincidence, we just got lucky. These 5 data points are like very close to the line, okay? These 2, we got a little bit of error. And so if we calculate the mean squared error on this validation set, right? We find these sum of squared errors for these 7 and we divide by 7. We're gonna get 0.0319. Okay. Is that all right? Okay, and now here again, this is the full set. These 7 are the observations. So this is fitting a quadratic model on the remaining 21 data points. Here is the other 7, and we say, okay, how much error is there here? Okay, all right, and so we can see, okay, now we've got a little bit of error here and some error here and some error here, and this is, we get mean squared error of 0.025, okay? So we fit it on the remaining 21, a quadratic model, and then this is the error that we get on the validation set. Okay, we're gonna look at the other 21 data points and fit a cubic model. So this is this is how a 3rd order polynomial goes, okay? And then this is the errors that we get when we fit this. Okay, are there any assumptions we have to make about the data before we do cross-validation? You have to worry about your assumptions a little bit less when you do cross-validation, okay? Obviously you don't want to fit bad models, but But cross-validation, the strategy here is think less about why the model works and just you are evaluating a model not so much on assumptions you are making, but you're evaluating a model on just, is it able to make good predictions, right? So I think last week I talked about a couple different strategies, one being, what's important to you? Understanding, explaining the variation in a way that you can understand, or just being able to make predictions, okay? And cross-validation is leans more on the prediction side. And we're just gonna say, if it can make good predictions, it's a good model. And if it can't make good predictions, it's not a good model. That's kind of what we're doing. Okay, so here's the cubic model fit on the 21 data points in our training set. These are the predictions that we make on the remaining 7 validation points, okay? Here's a 4th order polynomial, okay? And so you can see every time I increase the thing, you know, our curve gets a little bit more curvy, okay? And here's the errors that I get here, okay? Here's an 8th order polynomial, and with the 8th order polynomial, I'm able to you know, really predict this last point quite good, okay, quite well. And our line is a lot more wiggly, and you know, just visually we can say, you know what, this is probably not a good set, okay? And so the 8th order, every time you increase the number of predictors in your data set, you can decrease the error on your training data. But what happens is that, you know, you increase the errors in your prediction data, okay? So, you know, this last observation, according to 8th order polynomial, this line shoots up right here, okay? And so, so this prediction is probably not very good, right? This 8th order polynomial is basically saying that race times is going to get longer after the year 2012, which just doesn't make sense, okay? And then just to be silly, I tried fitting a 17th order polynomial on the training data, okay? And so you can see what this 17th order polynomial does is it's going to predict some of these data points, okay? Like these 3 data points, it predicts perfectly, okay? And you get this really wiggly line that minimizes a lot of these errors, okay? These errors have very, very, very little error, at least for the data that we have observed here, okay? These things, okay? But the data points that we have left out, okay? So like there's no data points here and here and here, and here we can see, you know, look how much error there is, right? So because the 17th order polynomial is basically predicting, there were no data points here, and so it's predicting like a huge dip here, and that doesn't make any sense. And so you got big error here, and this last observation, it has a tremendous amount of error. So it goes, you know, way off the chart, and so the mean squared error on this validation set is this ridiculously huge, you know, 1,600. Okay, so this is no good, right? And so if we keep track of all of these things, okay, so this was the cross-validation error that we got on validation sets A, B, C, and D, okay? And you can go through the slides and you can see that all of these numbers for validation set C is the same or matches up. And if you look at the different data sets, okay, you're gonna get different kinds amounts of error. And we can see that the cross-validation score here is going to be the average of these things, okay? So for whatever reason, validation set D in this run, validation set D probably includes this last observation here, this one right here, which is a little bit of an outlier. And so, you know, that one happens to be the biggest for all of these things. And so we get different amounts of error, and we would take the average of these things to get our cross-validation score. Okay. Oh, something happened. Okay, so just coincidentally, the 8th order polynomial, okay, happens to have the lowest cross-validation score. So, okay, for whatever reason, when I rendered this, it used to be the third order one, okay, 0.057, but in this case, coincidentally 0.0419. So we know, you know, just visually and logically thinking, we know the 8th order polynomial is not going to be the best. But but here, you would look at these average cross-validation scores, and you would say, okay, which one has the lowest average cross-validation score, okay? And here you would actually say, oh, maybe the 8th order polynomial is good, okay? But then you'd go, well, does that make sense? And then probably not. And so in this case, we would look at this and we would look at this, and our contenders would be the 3rd order and 8th order polynomials, okay? Now, in general, it's good to kind of just run the thing again. And so here, I run it again using a different seed, okay? And this time, the 3rd order polynomial performs the best, okay? And the 8th order polynomial performs poorly. And we can also see the 17th order polynomial always performs, absolutely the worst, okay? So here, the 3rd order polynomial performs the best, and we would choose the 3rd order polynomial. And then here's another run, okay? And in this case, the 3rd order polynomial, this is its performance here, okay? And it is also the lowest, okay? And so you can see, depending on the seed, it's possible to get different cross-validation results, okay? Where suboptimal models happen to perform best, right? So back here, the 8th order polynomial just happened to perform best in this cross-validation split. And in this case, and so it's possible to get a cross-validation result, where suboptimal model happens to perform best. And so if you're able to afford running the cross-validation multiple times, it's recommended that you do, just in case it tells you to pick a particular model, right? Is it coincidental that the cubic model has the best cross-validation score? I would say no, okay? So we've run it 3 times, okay? And in all 3 times, the cubic model is either the best or the 2nd best, okay? And is just in one of those runs, the 8th order polynomial is the best, okay? And in the other cases, it's, well, I guess in this case, it's the 2nd best. But in general, the 3rd order polynomial, the cubic one, is the best here, it's the best here, and it's the 2nd best in this one, okay? And so based on those results, okay, and generally we favor simpler models, okay, we would probably go with the 3rd order polynomial over the other ones, right? If we look at the linear fit, okay, its cross-validation score is among the worst performing ones, okay? And then the quadratic fit, doesn't seem to do great, okay, as far as you taking the average of these things. All right, you can do this with the GLM, cv.glm function, okay? And this is what you would do in production, okay? Again, in your homework, you're gonna have to do this manually, kind of the way I did. But in production, you would not code it up manually, and you would use cv.glm. And this time you would specify k equals to 4 or k equals to something else, okay? And it's gonna calculate this score here, okay? And we're gonna get values that are similar to this, but ever so slightly different. So here is 4-fold cross-validation on a linear model, okay? And we're gonna get values on the order of 0.064, 0.0659, 0.057, okay? There's gonna be slight variation in each of these runs because every time you run it, which observations end up in your validation set will be slightly different, okay? Oh, you know what? I'm running out of time. Let me give you the second quiz answer. The second quiz answer is C as in cat. Second quiz answer is C as in cat. All right, and okay, so anyway, this is a cross-validation run on the linear model. Here it is for the quadratic model, okay, and we can get slightly different scores. And then here it is on the cubic model, all right? And so you kind of compare values, okay? And you would say, okay, well, and that should help you make your decision as far as which model to use. When you do leave one out cross-validation, okay, you're gonna get the same value each time, okay? Because when you do leave one out cross-validation, the validation sets are identical, right? Each observation serves as the validation set exactly one time. So no matter how you run it or what you set your random seed to be, you're going to get the same value for leave one out cross validation. Okay. If the cross validation score is similar in two models, are there tiebreakers to consider? You know, probably then you would have to think, okay, just you'd have to balance, you know, do I prefer the simpler model or the more complex model? Do I, you know, does this one use logs, and do I want to have to use logs or not? Things like that. You know, always, if you've got a little bit of domain knowledge, just ask yourself, does it make sense that there's a quadratic relationship? Does it make sense that there's a cubic or fourth order relationship? And if you can think of a reason to justify such a relationship, then yeah, go with that thing. But if you don't have domain knowledge, then you know, a lot of these tiebreakers will just feel a little bit arbitrary. Okay. All right. So just a summary of all of this cross-validation stuff. It's a way to kind of to see how you know, one particular model will generalize to new data that you haven't seen, right? You've trained it on a certain set. You're going to see how well it predicts new observations, and this will help us flag problems like overfitting, right? So when you fit the 17th order polynomial, it fits the observed data and the training data really well, but it's overfitting it so that when you try to give it new data points, it does a really terrible job predicting it, okay? And the recommendation is to perform, you know, kind of multiple rounds of cross-validation, different partitions and things like that. Okay, we'll end here for today, and your homework will deal with cross-validation, and so take a look at that. You know, I hope, even though it's a lot of work, I hope it'll at least be an interesting problem to solve and try for. All right, you guys, we'll see you guys on Wednesday.